mark the memory as clean, and then just continue. And for the end results, we also take note of these branches because they are candidates for the OET with certain limitations. As I said, we only want the first branch to such a memory region because when it then goes into a loop and does something else, this is not likely a OET. And for reconstruction or automated reconstruction purposes, we only want to take note of branch types within the original process images, because this is how most unpackers or run attackers operate. This is due to the fact that not every executable can be easily relocated in memory, so the unpacker just creates a new executable, specifies where in memory it's supposed to be, and reserves space in memory as a section where the code is executed, unpacked into and then executed. And this is to guarantee that the unpacked code is right where it's supposed to be from the perspective of the original executable. It is theoretically possible to also just unpack to the spec. Whatever, and this can also be analyzed because these are also dumps, but for automatic recovery in the end, post-processing from the database, these events are not so important. And as I said, we might operate in multiple stages. We hope that at some point of time the process will stabilize, and then the last such OET candidate is the most likely actual OET. This brings us to the next question: when can we stop monitoring? This is unfortunately undecided in the general case. We cannot automatically and guarantee decide whether a process is done or is not yet done unpacked. And well, we need to find a way to determine a reasonable point of time where we can stop unpacking. And we can easily guarantee termination by just saying, well, here you can run for 30 minutes and then we just stop. But this is just an upper bound for execution time. And before that happens, we can track whether a process actually shows progress, which is the concept I call innovation. Innovation is whenever there's something new going on within the process. Say it loads a new dynamic link library. This means there's new code in the process image and it can potentially execute some new functionality. Same goes for modified code that's executed. There's also new code in memory that has potential to do some more. Slightly different, but at least the sign of innovation is when the process executes a function that wasn't executed before. Because I keep track of all branches from within the process or the executable image to a DLL, and whenever that function within the DLL has not yet been seen, this is also something new that's going to happen, that the process calls for new functionality within the library. And as long as there's some innovation, I just keep going and let the execution continue. And simulation is only stopped when, well, after the time limit, or when no process showed innovation for a certain amount of time, or no monitored process. So I count time in this case in just process switches, because that scales fairly well with simulation speed. So say you have 1,000 process switches and none of the monitored process did anything new, I say, well, okay, that's good enough. We just stop here. And after reconstruction, after termination, we of course want to unpack or reconstruct our original key images. So I want to leave the memory dump as modified as possible, just so that I don't lose much information. The nice thing about the keys file format is that headers can actually be mostly anywhere. You have the old XD header. I think, if I recall correctly, at the end of it, there's the P signature offset, which points to the actual PDA header. So what I can do is just take the original headers from the memory dump, append them to the end of the dump, and just modify the single value pointing to the PE signature, make that point to the new headers, and then just modify them, because that's as good as modifying the original ones, but I keep the original ones intact. Then I modify the entry point. That means I saw the last branch to that memory region that led to the dump, set the entry point to that address, and then I adjust the on disk alignment. See it here? Well, not quite. You might remember this picture. It's supposed to be actually red and blue and stuff like that. You have the on disk format, the zero palette, same here, back zero padding, because this is aligned to section alignment. And when we now take a memory dump, the red time. Okay. What we do is we remove, we dump this to this as is. We say, well, we don't need this kind of section file alignment. We can just use the long file alignment, which is perfectly legal. So we don't have to modify anything in there. We append a new section called Pandora. Can be any arbitrary name. Just make the PE signature offset point to the new headers, and then append all kinds of import information that we want to reconstruct. The most important part here is the so-called import address table. It basically describes which library functions the program needs. So this is also important for analysis of